Hello, math learners. In the previous two videos, we looked at the radius of convergence for a power series. And we did that by using the ratio test and using our logic. Now we're going to still look at the radius of the convergence for a power series, but we're going to just pretty much summarize it all on the screen all at one time. So our big goal here is we have a power series and we're trying to find the radius of convergence. Or in other words, if we look at the interval of convergence for this power series, meaning the values of x that make this power series converge, we want to look at the radius of that interval. Or in other words, we're looking for the half width of the interval of x's that make this power series converge. So what we do is we use the ratio test. Remember, with our ratio test, we're looking at the limit as n goes to infinity of the absolute value of an plus 1 over an. So when we use the ratio test for a power series, there are three results that can come out. One of the results is that this limit can equal 0. Another result is that the limit could equal infinity. And the last result is the limit could equal some constant k times the absolute value of x minus a. So if we end up with the limit of the absolute value of the ratios is equal to 0, then that means that the series converges for all the values of x. Now, if the series converges for all the values of x, then that means that our interval goes from negative infinity to positive infinity, so our radius of convergence is infinite. Okay, so we've looked at the first setting where the radius of convergence is infinite. Now let's look at what happens if our limit as n goes to infinity of the absolute value of an plus 1 over an is equal to infinity. So this limit is infinite. That means that by our definition of ratio test, or by our rules of the ratio test, that our series diverges. So no values of x are going to make this series converge. So our radius of convergence is 0. Now, finally, we have the setting that we looked at in the last couple examples. Our limit is equal to some constant times the absolute value of x minus a. So this means that the series will converge as long as k times the absolute value of x minus a is less than 1. So our radius of convergence is 1 over k. That's my husky, thank you. All right, so let's look at an example that's a little bit different from the other two examples that we looked at earlier. So here is our power series that we're working with, and we want to know what is the radius of convergence for this power series. All right, so an is equal to x to the 2n minus 1 times negative 1 to the n plus 1 over 2n plus 1 factorial. And we also need to know an plus 1. So what we do is we go through and wherever we saw an n, we replace it with n plus 1. So we've got 2 times n plus 1 minus 1. We've got negative 1 to the n plus 2. And then we've got 2n plus 1 factorial. So let's clean this up a little bit. We've got x to the 2n plus 2 minus 1. So we've got x to the 2n plus 1. We've got this positive negative 1 thing going on, but really actually, let's just forget about that because this has absolute values anyway. Let's just throw the absolute values on right now. And then in our denominator, we have 2n plus 3 factorial. Okay, so let's go ahead and use these bits to find the limit as n goes to infinity of the absolute value of an plus 1 over the absolute value of an. So copying it down, we've got, just adding some absolute values really quick. So we've got absolute value of x to the 2n plus 1 divided by 2n plus 3 factorial. And then an is right here. So copying that over, I'll just make a little space here. So copying that over, we've got 2n plus 1 factorial over x to the 2n minus 1. All right, so let's go ahead and start to cancel some things out. Let's start with the 2n plus 3. 2n plus 3 factorial. By our definition of factorial, that's equal to 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So that means that 2n plus 3 factorial is going to cancel out with 2n plus 1 factorial and leaves us just a few of these terms here. Next, let's work on canceling some stuff out with the x to the 2n plus 1 and the x to the 2n minus 1. So if we think about x to the 2n plus 1, that's equal to x to the 2n minus 1 plus 2 more. Or in other words, this is equal to x to the 2n minus 1 times x squared. And that's useful because we have x to the 2n minus 1 here, and so we want to have this piece cancel out with that. So let's put that all together. Our numerator is x to the 2n minus 1 times x squared. And then here we've got 2n plus 1 factorial. Our denominator, let's write this more. Our denominator then, we said 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And then we have the x to the 2n minus 1. So now we can go ahead and cancel some stuff out. X to the 2n minus 1 cancels. 2n plus 1 factorial cancels. And that leaves us with the limit as n goes to infinity of x squared over 2n plus 3 times 2n plus 2. Now when we send n to infinity, we are making the denominator grow without bound. So this entire fraction will go to 0. So since this goes to 0, that means that the ratio test says that this series will converge for all values of x. So since this series will converge for all values of x, that means that our radius of convergence is infinite. All right, so just to summarize, we use the ratio test and we look at the limit as n goes to infinity of the absolute value of an plus 1 over an. If that's equal to 0, then our radius of convergence is infinite. If our limit is equal to infinity, then our radius of convergence is 0. And if our limit is equal to constant times the absolute value of x minus a, then that means that our radius of convergence is 1 divided by that constant.